Hello, students, and a very warm welcome to all of you. Today, we are going to look at a topic which, well, many students find it a little tricky. But I promise you, once you understand the basic idea behind it, it becomes very, very logical. We are talking about the physical properties of haloalkanes. Now, I want you to think about something you might have seen in your chemistry lab. Imagine you spill a little bit of some chemical, and poof, it just disappears. It evaporates in minutes. But then another puddle of a different chemical, it just stays there for hours, right? For example, a little chloroethane disappears very fast, but a drop of iodoethane will remain for a very long time. So what is happening here? Is it some kind of magic? No, not at all. It is pure, simple chemistry. And by the end of our discussion today, you will understand exactly why this happens. You see, the answer to that puzzle, and also to many questions that come in your board exams, is all about understanding the physical properties of these haloalkanes. And this is not just for scoring marks, mind you. This is very important for real-world things, like which haloalkane will be a good solvent, or which one can we use as a refrigerant in our ACs. So to understand all this, we need to look at a kind of battle happening at the molecular level, a battle between two main factors. Okay, so at the most basic level, physical properties like boiling point are decided by a competition. On one team, we have the molecule's total weight, its molecular mass. And because of this weight, you get what we call London dispersion forces. These are just weak, temporary attractions. And on the other team, we have the molecule's polarity. This creates what we call dipole-dipole interactions, basically attractions between the slightly positive and slightly negative ends of the molecules. So just think of it like this. It's a tug of war. On one side is the molecule's weight, and on the other side is its, let's call it magnetic nature, or polarity. Who wins this tug of war decides the boiling point. All right, let's take a very simple example. Look at ethane. It's a simple hydrocarbon, right? It's not very heavy, and it is nonpolar. Now, what if we take out one hydrogen atom and we put a chlorine atom in its place? We get chloroethane. So what have we done? We've actually changed two things. Think about it. First, by adding chlorine, we have made the molecule heavier. And second, because chlorine is very electronegative, we have introduced polarity. That CCl bond is now polar. So we have added both weight and polarity.
Okay, to make this idea really simple and easy to remember, let's use a nice analogy. It will help you visualize what is actually happening with all these molecules.
I want you to imagine a large crowd of people, maybe at a concert or a festival. Now, first let's think about ethane molecules. These molecules are like very lightweight people in that crowd. They are like feathers almost, and they have no reason to stick to each other. So it takes almost zero energy to separate them, right? The crowd just breaks apart and disperses very easily. And that is exactly why ethane has such a low boiling point. But now, let's see what happens with chloroethane. Things are different here. These molecules are like heavier people in the crowd. And not just that, imagine each person is wearing a magnetic badge. What do magnets do? They attract each other. So because of these magnetic badges, which represent our polarity, the people will stick together. They will form clusters. Now, to break this crowd apart, you will need to apply more force, more energy, which means more heat. And that is why chloroethane has a higher boiling point than ethane. And finally, let's talk about iodoethene. Now, these molecules are like very, very heavy people in our crowd. Super heavy. Interestingly, their magnetic badges are actually a little weaker than chlorine's. But that doesn't matter so much, because their weight is just enormous. The crowd is so dense, so heavy, that it is extremely difficult to push these people apart. The most important thing here is their weight. Their sheer weight is the main reason they are held together so strongly. So, this whole story about the crowd, what we are actually describing are the intermolecular forces. These are the forces of attraction between the molecules. And the logic is very simple. The stronger these forces are, the more energy, the more heat you will need to pull the molecules apart, to change the liquid into a gas. So stronger intermolecular forces means a higher boiling point. It's as simple as that. All right, so now you're thinking, okay, I've got this. Both polarity and weight are important. But there is a common mistake that students often make. Let's look at that now so you can avoid it. So think about this for a moment. We all know that fluorine is the most electronegative element, right? It's the king. So the CF bond is the most polar bond. It is very logical to think that, well, if it's the most polar, it must have the strongest magnetic attraction. So shouldn't fluoroethane have the highest boiling point among all the ethyl halides? It seems logical, doesn't it? But let's look at the real data. the facts tell a completely different story. The reality is the exact opposite. Look here. Fluoroethane boils at -37 degrees Celsius. It's a gas, even in a cold room. But iodoethane boils at +72 degrees Celsius. That's a difference of more than 100 degrees. So clearly, our first thought was wrong. So what is really happening here? Well, the answer is molecular weight. You see, an iodine atom is almost 7 times heavier than a fluorine atom. This huge difference in weight creates very, very strong London dispersion forces. And these forces, which come from the sheer size and mass of the molecule, are so powerful that they just completely dominate. They overpower the effect of polarity. Going back to our analogy, the super heavy crowd is just much, much harder to break apart than the lightweight crowd, even if that lightweight crowd has stronger magnets. So here is the most important rule you need to remember for your exams. When you are comparing haloalkanes with different halogens, the deciding factor is almost always the mass. In this battle between molecular weight and polarity, for haloalkanes, molecular weight is the clear winner. It's the heavyweight champion. Okay, so why is this important in real life, not just for our exams? Well, understanding these physical properties is absolutely critical for technology. And let's take a perfect example: the chemicals used in our refrigerators and our ACs. For many, many years, a chemical called CFC12 was the standard refrigerant. Now, why was it chosen? It was chosen specifically for its physical properties. It had a boiling point of around -30 degrees Celsius. This was perfect because it allowed it to easily vaporize and absorb heat from inside the fridge, and then it could be compressed back into a liquid to release the heat outside. But there was a very big problem. We discovered that these CFCs were creating a hole in our ozone layer. So scientists faced a massive challenge. They had to find a new chemical that was safe for the ozone, but, and this is the crucial part, it had to have almost the exact same boiling point as the old one. Why? Because then it could work in the millions of refrigerators and ACs that were already built. And they found one, HFC 134A. Its boiling point is -26 degrees Celsius, almost a perfect match. This really shows you how important physical properties are for real-world engineering. All right, so let us quickly summarize the main takeaways from our discussion today. First, remember that physical properties are decided by a battle between molecular weight and polarity. Second, as we go down the halogen group from fluorine to iodine, the molecules become much, much heavier. This leads to stronger intermolecular forces and therefore higher boiling points. And the third and most important point, in this battle, molecular weight is almost always the winner, the dominant factor. And if you ever get confused, just remember our analogy of the crowd at a concert. It is always harder to disperse a crowd of very heavy people. That one simple mental picture will help you get the correct answer for the boiling point trend every single time. So I will leave you with one final question to make sure this concept is locked in your mind. The next time you are in an exam and you have to compare the boiling points of 2 different haloalkanes, what is the #1 factor you should look at first? That's right, it is the molecular weight. If you just remember this main idea, our simple crowd analogy, and the real-world example of refrigerants, I promise you this topic will feel so much easier in your exams. Thank you so much for joining me today.